Hi, I'm Bob. Welcome back to the 5 Minute Econometrics, an econometric tutorial on basic concepts and estimation methods. Today, we will explore the linear in parameters assumption for the population model. The linear in parameters assumption is for the population model. It is one of the classical linear model assumptions. All the classical linear model assumptions are for the population model instead of the estimated model. You can refer to my previous video for an explanation of the difference between the population model and the estimated model. The population model is also called the underlying data generating process. It represents the real relationship between the explanatory variable x and the outcome variable y. The population parameters describe the ceteris paribus effects or the causal effects of the explanatory variables on the outcome variable. The linear in parameters assumption means in the population model, the outcome variable y is related to the explanatory variable x and the unobserved random error term mu in a linear form. The key is that it is linear in betas rather than the variables. Betas are the population parameters we want to estimate. It can only take the level form. It cannot take a squared form or logarithmic form. By contrast, the variables in the model can take arbitrary functional forms, such as logarithms or squares. In other words, nonlinear relationships between variables are allowed in the model. Nonlinear relationships between models often appear in econometric analysis. We use the logarithmic form of variables, such as log wages and log profit, to capture the percentage change in each variable. When the outcome variable is in the log form, the slope parameters are the effect of 1 unit of the explanatory variable on the percentage change in the outcome variable. When the explanatory variables are in the log form, the coefficients represent how much the percentage change in the explanatory variables affects the outcome. When both the explanatory variable and the outcome variable are in the log form, we call the model a constant elasticity model. That is, the parameter describes a constant marginal effect in terms of percentage change. For example, we used the sample of US workers in 2017 to find the association between workers' wages and their parents' earnings by regressing the workers' log wages on their parents' log income. The OLS estimate of the slope is 0.35. It implies that as their parents' incomes increase by 10%, the workers' wages increase by 3.5%. We use the squared form of the explanatory variables to capture a quadratic relation between the explanatory variables and the outcome variable. This model allows the effect of years of schooling on wages to be non-constant. It can capture the diminishing returns to education or the increasing returns to education. In other words, it allows the effect of education on wages to change with years of schooling. The partial effect of education on wages, partial log wage over partial schooling equals beta 1 plus 2 times beta 2 times years of schooling. We use the same dataset to estimate the returns to education by regressing the log wage on years of schooling and its squared term, along with other control variables that are also associated with wages, such as gender, marital status, and region. We find an increasing return to education. The range of years of schooling in the sample is from 6 to 17 years. For workers who have only completed elementary school, an additional year of schooling increases wages by approximately 5%. For workers with a high school diploma, an additional year of schooling increases their wages by 11%. For their counterparts who hold a bachelor's degree, one more year of schooling increases their wages by 15%. For the workers who have received graduate education, the returns to education are even higher. The returns to education are nonlinear in this model. In today's topic, we have discussed one of the classical linear model assumptions, linear in parameters, and have explored some models that satisfy the linear in parameters assumption, but can capture nonlinear relationships between variables. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.